Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is shortest XY distance in grid, and it is a medium level problem. So this particular problem is a standard problem called the multiple source shortest path problem, and in this problem it says that we have been given n into m grid of characters O, X and Y, right? And we have to find the minimum Manhattan distance between X and Y. So Manhattan distance is the absolute difference between the rows or the X indexes and plus the absolute difference between the Y indexes, that is the column indexes. So basically, for example, this particular test case, here are some X and Y's. We have to find the shortest distance between any two X and any two Y's. So if you see that this particular X is at a distance of 2 to this particular Y, right? You can go from here then here. So that is at a distance of 2. Now this particular distance X is at a distance of 1 to 2 of the Y's. So one Y is on the top of it and one Y is at the bottom of it. So it can reach both of the Y's in one distance. So since this is the smallest distance possible, the answer is 1 in this case. Similarly, in this particular test case, what is happening is these are two x's and one y is here, one y is here. From this particular x, you can go you can travel 2 units of distance downwards and you can reach this y. And from this particular x, you can go one step downward and one step right, then you will reach the second y. So in both of the cases, the minimum answer is 2, and this is the minimum possible answer in this particular grid. So there are actually a number of ways to solve this particular problem, and since it is a very standard problem, so let us not dive into the solution directly. First we'll discuss what are the different ways of solving this problem, right? So the first way, which is not so optimal, this is just I'm just telling you just to explain you what are the different ways, but this problem is not very optimal and you will never use this particular way, right? So in this particular way, what you do is you do normal BFS. For example, you have a source, you have multiple sources, right? So all the indexes ij where grid of ij grid of ij grid of ij is equals to x is called a source, and where all the indexes ij where grid of ij is equals to y is our destination, right? So we make a list of all the sources. So we will have i1 comma j1, we will have i2 comma j2, we will have i3 comma j3, and so on, right? We will have this list continually going on. So first of all, we will take this particular element i1 and j1 and start our BFS from here. So you must already know how to use the BFS and how to find shortest path using BFS. So we have converted this particular problem of multiple source shortest path into single source shortest path. So we will only take one source at a time and compute the distance of all the indexes, and we will find the minimum distance among all the destinations such that grid of ij is equal to y. So this is called a destination, right? Again, we do it for i2, j2, and again we find the minimum from the previous ones now as well as from the current ones, right? Again we do it for i3, j3, and again find the minimum among all the indexes ij such that grid of ij is equal to y. Or we can also say that grid of ij is a destination, right? So in this particular scenario, what we do is we just follow single source shortest path strategy and we consider only one source at a time, right? So this is the most simple and naive approach you can follow to solve these kind of problems, but the time complexity associated with it is very huge, right? So this is not very optimal and you shall never use it. So the second method, that is to use Dijkstra's algorithm. So how do we use Dijkstra's algorithm? If you have used if you know about Dijkstra's algorithm, you must have heard that it is generally used on a weighted graph, but this graph is unweighted. So how do we use Dijkstra's algorithm on an unweighted graph? So you see that for example, if I have something like this, and for example my 1x is here and my 1x is here and my 1y is here, right? So let us just say that this particular x, the top one, updated the distance of this particular y as 2, right? So although it will never happen in this order, but let's just say that this particular x updated the index of this particular y as 2. So it's a it says that the distance of this particular minimum distance of this particular y is 2, right? Now the very like crucial condition that we generally use in Dijkstra's algorithm is if distance of ij, where ij is any cell in our grid, is greater than current distance plus the weight. So since this is an unweighted graph, we can take all the weights to be 1, right? So whenever the distance of ij is greater than current distance plus 1, we just update the distance of ij. So this, according to this x, the smallest distance of y is 2, right? Because it is 2 steps, 1 and 2. But for example, now this particular x comes, it says that the distance of this particular y is less than the current distance plus 1. So the current distance of this particular x is 0, right? It is at 0 position since it is a source. Now if you add 1 to it, so the distance of this y is 1, which is less than the original distance that the current element is having, that is 2, right? So in this case, we will update the distance of y and push it into the queue, or the priority queue we maintain, right? So this is the Dijkstra's algorithm and how we are going to use it, and basically why does it work in this particular scenario even if it is an unweighted graph. This is because instead of a single source, there are multiple sources right now, and each source can have a different distance value for the same y. So for example, this particular x has a distance 2 from this particular y, and the second x has a distance of 1 from this y. So if it has a smaller distance, then we should allow it to update the distance of y, and then similar to the Dijkstra's algorithm, we push this particular element y with the distance, along with the distance, into the priority queue. So the expected time complexity of Dijkstra's algorithm using a priority queue or a max heap, min heap, whatever we can call it, because the priority queues in C++ are implemented according to heaps, right? So the expected time complexity is V plus E, right? Plus some constant time. I would not say it is constant. Actually, it depends on the number of operations done on the priority queue. So let us just say it is some value alpha, right? So the number of the deletion of elements in priority queue is log n, the insertion is log n, and accessing is O of 1, right? So this is deletion, this is insertion, and this is accessing. It is just similar to a heap. So like the number of vertices in our case is 10 raised to the power 6. The number of edges is 10 raised to the power 6 into 4, since from each grid we can go into 4 directions except the corner grids or the grids with the corner, but let us just ignore that. So this is like not very huge. It is 5 into 10 raised to the power 6, and it should have passed, but I believe this alpha is like way huge for this particular problem. Generally what happens is the Dijkstra's algorithm in these kind of problems works, but when I tried to submit this particular problem using Dijkstra's algorithm, it didn't work. So that is why I'm explaining you this time complexity of this particular problem. Since it is like way less than 10 raised to the power 8, it should have worked, but I believe this is where it went wrong. And Dijkstra's algorithm will not work if you try to submit it. At least my code didn't work when I tried to submit it. It gave me TLE on around test cases like 687 or something. So let us discuss another approach without using the Dijkstra's algorithm, right? So what happens in this particular approach is, as I've already explained you, that this particular scenario will never occur while I was explaining the Dijkstra's algorithm, that this x updates the value of y as 2, and then later this x will update the value of y as 1. So this particular order will never occur in such a, if you do BFS, right? Why? I'll explain you. So what happens is BFS is, for example, you have multiple x. One x is here, one x is here, right? So let us just take like this. So if we do like BFS, now let us, instead of doing single source shortest path like we were doing in the first case or the first approach, now let us just do multiple source shortest path. Now we are not maintaining a priority queue, we are just maintaining a simple queue and just pushing all the sources, that is these two elements, into my queue. So I'm just maintaining the queue. So what happens is, whenever we do BFS, if you have studied about BFS, it generally expands in according to the radius. So for example, if x is at here, during the first iteration, it will go here, it will go here, it will go here, and it will go here. Right? During the second iteration, it will go here. Then from here, it can go here. It can go here. It can go here. It can go here. So you see, if there was a cell right here also, it could have also gone here. So you see, at each step, the area of x expands in a radius, right? And this is true for all the x's. So for example, if one x is here, one x is here, in the first iteration, the radius will be a circle of unit 1. So it is not exactly a circle. I'm just saying it. So in the first instance or iteration, it will cover all the boxes or all the cells at distance 1. Then it will cover all the cells at distance 2. Then it will cover all the cells at distance 3. Similarly, for this particular box x also, or this particular source also, it will cover all the cells at distance 1, then all the cells at distance 2, then all the cells at distance 3, right? So for all the sources, we are covering each time a particular distance, right? First the distance is 1, then the distance is 2, then the distance is 3, then the distance is 4, right? So now what happens is, if this particular x, or this particular first x, let me call it x1 and let me call it x2. If this particular x1 was able to reach a particular cell before x2, that means that particular cell is closer to x1 than x2, right? Or it might be at equal distance also, then it depends on the ordering, right? But it should definitely be less than the distance of this particular cell from x1 should always be less than or equal to x2. I hope you are understanding what I'm trying to say. So at each iteration, first it covers a distance of 1, then it covers a distance of 2, then it covers a distance of 3. Similarly, for here also, it covers a distance of 1, it covers a distance of 2, then it covers a distance of 3. Right? If I am able to reach this particular cell, right, with x1 before x2, then definitely its distance is less than or equal to from x1, its distance is less than or equal to its distance from x2. So for example, let me just give you a different analogy. If two players are starting from these two different positions and they try to run towards each other, given that their speeds are same, right? So if I take any point, like if I take this particular point, if this player 2 and this is player 1, if both of their speeds are same, and if player 2 is able to reach this particular point first, that means this point was closer to player 2, right? If the element was exactly at the middle. So let's say both player 1 and player 2 reached here, right? But I asked player 2 first, have you reached? Then player 2 says yes, right? So in this case, player 2 will say yes first instead of player 1. But if I ask player 1, player 1 will say yes. So in this case, the order is important, right? Order will matter. It is not important. It's just that the order will matter. Which of those x1 and x2 or player 1 and player 2 says that I have reached, right? If the point is to the left, then player 1 will reach the point first since it is closer to the point. So this is the exact same thing I'm trying to explain you here. That is, each cell is expanding by a unit radius of 1, and whichever point reaches the grid first is the grid closest to it, right? So what we can just do is, we can just maintain a visited vector, a double dimensional vector or array, which will store whether the current cell has been visited or not. If the current cell has been visited, that means it has been covered by some source, right? If it has been already covered by some source, that means it was closer to that particular source first, right? Now even if I try to update its distance, it is not very optimal to update the distance, because it would always be greater than the distance it already has, right? So now what I do is, I just maintain a visited vector and I just do simple BFS, and if the cell is not visited, I just visit it and I'll update its distance. Otherwise, if the cell is already visited, I just ignore it. And as soon as I find a y, I'll just return the current distance, which will be my final answer. So let me just show you the code for it now. So what I've done is, I have taken a distance and the visited vector. So this particular I have declared as arrays here. So this will store the distance of the current cell, and this will store the whether the current cell has been visited or not. Right. So what I do is, I just maintain a queue of pair int comma int. So this will store all my cells in the queue, right? Now I just run a for loop through the whole grid. If the current element is x, I just push it into my queue. Since this is a source, I just set the current distance as 0, and I set I just said that the current element has been visited. Now otherwise I just set its distance as some random value, and I just set it as unvisited. So while the queue is not empty, I just create two variables x and y. So this will denote the current cell, right? So the current cell will be at q dot front, and I just initialize those values, and I just pop the front element from the queue. Now for all four directions, so if you have already done grid BFS or grid DFS, you must be familiar of this technique where we initialize two arrays dx and dy. So I've initialized them here. So actually we only need up to 4 values, but I just wrote all of the values just for your understanding. So this is a very popular technique. So in this case, I've also commented what are the directions these values correspond to. So for example, if you decrease the x value by 1 and do not change the y value, you will actually move one step upwards in the grid, right? If you increase the x value by 1 and do not change the y value, you will actually move one step downwards in the grid. If you do not change the x value and decrease the y value by 1, you will move one step left. And if you do not change the x value and increase the y value by 1, you will actually move one step to the right. Right. Similarly, for all these values, up left, up right, down left, and down right. If you subtract both of those values, x and y by 1, you will actually move up left. So this is a combination of up, this particular value, and left, this particular value, right? So similarly, the whole thing works, and this is like very convenient to use. Instead of forming 4 different conditions, you can just form a for loop and find out the new x and new y, which will be the new positions. Now I just check if this position is valid. Valid means I just check if it lies inside my grid or not. So if the x index is less than 0, or it is greater than or equal to n, or it is less than 0, y index is less than 0, or y index is greater than or equal to m, then it means that exists outside the grid, and I can just return 0, otherwise I return 1. So this way the code is very clean, and I don't have to write the different conditions here only. That is why I do these kind of thing. I have created a valid function, and I check whether the current new node I'm trying to visit is visited or not. So once it is valid, then I check it is visited or not. If it is not visited, then what I do is I update its distance by the distance of the current node plus 1 will be the distance of the new node, right, or the new cell. So I just mark the new cell as visited, and I check if the new cell has the character y. That means this is one of my destinations. So if I have reached my destination, I can just return the distance of my destination, right? And otherwise, what I do is I just push my new cell into my queue. So this will continue keep on going on, and we will encounter one of the wise ones, and if you encounter it, this will return from here. So this was the solution to the problem, the shortest xy distance in grid. Since this was a very standard problem, I tried to explain you what are all the possible ways that you can solve this problem with. Although some of these ways are not very optimal to solve, and some ways like Geeks algorithm would generally work in other problems, but it did not work in this particular problem. It was giving TLE. So I've explained you all the 3 different ways. So the last way worked in this particular problem. So I hope you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to subscribe to the channel. It's always free of cost, and if you don't find the content interesting later, you can always unsubscribe. So till the next video drops, keep coding, stay safe, bye bye.